The memory system is a fascinating topic for discussion because it incorporates several neat and interesting ideas. This video will introduce the memory system and will show the perspective of the memory system being a hierarchy of caches. Memory systems are not only interesting but are also very important. If you recall the von Neumann architecture of a computer, the memory system is the second most crucial part after the main processor. In the von Neumann architecture, memory is used for storing both instructions and data. In fact, today, memory systems are more important than processors because memory systems are the bottleneck in performance. Processor performance has been increased to such an extent using various techniques that today memory performance is the bottleneck, and hence applying more and more techniques to improve processor performance without improving memory performance is of no use. Furthermore, for fundamental reasons, we cannot really improve the performance of memory systems by simply throwing more hardware or more gates at the problem. Just to give you an idea of the kind of numbers we are talking about, memory access latency today can be 20 nanoseconds or more. This is the random access memory we are talking about. When you buy a computer or a phone, you hear about it having 1 GB memory, 2 GB memory, 4 GB, 8 GB, and so on. The access latency of this RAM, random access memory, can be 20 nanoseconds or more today. In comparison, you know that processor clocks today run at several gigahertz, which implies that the processor cycle is about a nanosecond or lesser. So clearly, from a program performance perspective, it is very important that we learn how the memory works, various techniques to make memory faster, and such design aspects of the memory system. So let us begin our discussion by asking the question of what the programmer wants. What the programmer wants from the memory system is that memory should be large to accommodate potentially large number of instructions and data. And of course, it should be fast so that the program finishes faster. And the programmer also wants that the computer on which the program runs be cheap. In other words, the memory should be cheap. Well, the programmer may want this, but the reality is something different. In reality, for fundamental reasons, large memory is almost the opposite of fast memory. The larger the memory unit, the slower it is going to be. Although large memory typically costs lesser per byte compared to smaller memory, larger memory is necessarily slow. So the design objective of the memory system can be stated in a single line as creating an illusion of large and fast memory. Large and fast memory is not possible in reality, so the memory system creates an illusion of large and fast memory. And this is the theme which we are going to see repeatedly as we discuss various aspects of the memory system: cache memory, main memory, virtual memory, and secondary memory, which really is input-output. The main technique used by the memory system in creating this illusion of large and fast memory is that of caching. So let us begin with the question of what is a cache. In normal English usage, what does the word cache mean? In normal English usage, the word cache means a safe place to store something. For example, you can talk about a squirrel storing a cache of nuts for the winter. Now, what does this word mean in a computer science context? In a computer science context, this word means a temporary place, usually a copy of something, and this copy helps in fast, easy, and efficient access to whatever is being stored. Can you think of other examples of caching you are aware of in the computer science context? As I said earlier, the idea of caching is central to computer science systems, and pretty much any system you can think of will have some caching involved. It will be difficult to think of a computer science system which does not have any caching. Although the word cache and the idea of caching itself are generic and find application in several computer science systems, in this course, the word cache, unless mentioned otherwise, is going to refer to something specific, and that something is a small piece of memory which sits in between the processor or the CPU and the main memory. So the picture you should have in mind is large main memory and a small cache which sits in between the processor and the main memory. The small cache is going to be much faster than the main memory. This small cache memory is going to be faster than the large main memory, not only because the cache memory is small, but also because it uses a different memory technology called SRAM as opposed to the main memory which uses DRAM. As to how DRAM and SRAM are constructed using transistors would have been learned in the prerequisite course on digital logic. Let us recall here the main differences between DRAM and SRAM which are relevant for this course going forward. Typically, DRAM design uses lesser transistors. It can use as few as just one transistor for a memory cell. On the other hand, static RAM uses many more transistors. A typical number here is 6 transistors per memory cell. There is a price though DRAM has to pay for using only one transistor per memory cell, and this price is in terms of the need to refresh the memory cell periodically. Without such refreshing, the memory in that memory cell can be lost. This need to refresh is the primary reason why DRAM gets its name dynamic RAM. Static RAM, SRAM, on the other hand, has no such need to refresh the memory cell. The need to refresh has an important implication that DRAM consumes more power than SRAM. And by design, DRAM has a much higher access latency. Access latency is the time between when you give the memory an address and when the memory location corresponding to that address is read. The access latency in DRAM can be 10 times or more than that in SRAM. Another factor why DRAM is slower than SRAM is in terms of the cycle time. The cycle time metric is different from the access latency metric. Cycle time is the time between two successive accesses. Ideally, cycle time will be the same as access time, that is, you can access one memory location after another. This is the case in the case of SRAM design. On the other hand, in DRAM design, you can have cycle time which is greater than the access time. This again arises due to the need for DRAM to refresh its memory cells. Despite these disadvantages, DRAM is cheaper. It has that big advantage. So DRAM is the technology which is preferred for building large amounts of main memory. SRAM on the other hand is more expensive and hence is used for building small amounts of cache memory. There is also another important reason why SRAM is used for the cache memory apart from the cost reason, and that other reason is that of lesser power consumption in SRAM. These days it is common to have cache memory integrated within the same chip as the main processor. So in such a scenario, it is important to have lesser power consumption. Otherwise, we would have to drain heat from the processor chip at a much faster rate. So in summary, there are 3 reasons why caches are faster than main memory. The first is that it uses different technology, static RAM as opposed to dynamic RAM. The second is that cache memory is smaller as compared to main memory. Smaller memory typically translates to faster memory. And the third reason is that caches are typically inside the processor chip itself, while main memory is outside the main processor chip. The processor can clearly access the cache faster because it is closer to the CPU inside the processor chip itself as opposed to main memory which is outside the processor chip. So we are going to use this idea of caching to create an illusion of large and fast memory. So why do we think that this idea is going to work? Why is this illusion going to work? The fundamental reason why caches work in creating this illusion is due to the principle of locality. Well, what is the principle of locality? There are 2 aspects to the principle of locality. The first is temporal locality. temporal locality says that if something is accessed now, it will likely be accessed again in the near future. The other dimension to locality is spatial locality, which says that if something is accessed now, the nearby locations to that something will likely be accessed in the near future. All this abstract definition is all fine. Can you now think of why these principles of locality, temporal locality and spatial locality, may apply for instructions which are executing in your program? Well, instructions are a clear case of exhibiting both temporal locality and spatial locality. The mere fact that instructions are executed sequentially mostly refers to spatial locality. And loops, which are common in many programs, give rise to the same set of instructions being executed in a loop, and this is nothing but temporal locality. Alright, this is with respect to instructions. Can you now think of temporal and spatial locality, whether they arise with respect to data access in typical programs you write? In the case of data, typical programming constructs such as arrays, structures, objects, they are all instances of spatial locality. Once again, variables accessed within a loop will be instances of temporal locality, and also local variables within a function give rise to temporal locality. That is, once you have defined a variable within a function, you are likely to access it many times within the function before that function returns. So, typical programs have very good temporal and spatial locality for instructions as well as data, and this is the primary reason why caches work. So here is a diagram depicting the memory system as a hierarchy of caches. Although we talked earlier about only one cache between the processor and the main memory, typically today you have at least 2 levels of cache, and in many computers even 3 levels of cache between the CPU and the main memory. This diagram shows 2 levels of cache between the CPU and the main memory. The one closer to the CPU is called L1 cache. The one further away from the CPU is called L2 cache. Many systems also have an L3 cache between the L2 cache and the main memory, but that's not shown in this diagram. As part of the memory system, we will also be learning about virtual memory. We will learn that the primary purpose of virtual memory is really to provide a level of indirection and all the flexibilities which come with this level of indirection. However, we can also view virtual memory or secondary memory as another instance in this hierarchy of caches. And in that perspective, we can view main memory as nothing but a cache for virtual memory. So in this diagram, we have L1 cache serving as a cache for L2 cache locations, L2 cache serving as cache for main memory locations, and main memory itself serving as cache for virtual memory locations. Do you think you can spot any other instance of caching in this diagram? Oh yes, indeed. We can view the registers which are present within the CPU as nothing but cache for the various memory locations. The size of this cache is very small. In the MIPS architecture, it is only 32 registers, and it is very fast, of course. So in this perspective, we can consider registers as yet another instance of caching in this hierarchy of caches. You should of course remember that this is only a perspective. Registers have very special meaning and they are not just a cache for memory locations. Registers are an integral part of the instruction set architecture itself. So the perspective that registers are a cache is true but quite incomplete. Likewise, the perspective that main memory is just a cache for virtual memory, that virtual memory is nothing but an instance in the cache hierarchy, that perspective would be correct but incomplete. So in this diagram, the first level of the hierarchy and the last level have special meanings. However, this perspective of viewing everything in the computer starting from the processor to the secondary memory or input-output devices as a hierarchy of caches is quite amazing, isn't it? To summarize, we have seen the memory system and in fact the entire computer as a hierarchy of caches, and we have learned that caching works to create this illusion of large and fast memory by essentially using this principle of locality, which is present in plenty in normal programs. Next, we will look at the various design aspects of constructing a cache.